So as we know that Professor Panda have already discussed this one. So here we can see that the tetrahedral structure is here of methane, but when the one proton abstraction takes place, it's become trigonal planar. So because the structure have changed here, trigonal planar, it's become has sp3 hybridization. Here it was sp3 hybridization here, and this is sp2. So because of that, the carbocation hybridization changed. So here you can see that the top view is you can see unhybridized p orbital, side view is this one. So carbocation is basically a trigonal planar structure. So let's talk about the classification here quickly, then we will solve the question. So methyl carbocations are the carbocation where the three hydrogen atoms are there, and this is also called a primary carbocation. Here you can see two hydrogen attached, and this is a primary carbon. That means the carbon which is attached to only one carbon, this one carbon, and two hydrogens are there. So that's why this is called a primary carbocations. And the other species is one hydrogen attached to the carb secondary carbocation, where the carbon is attached to two carbons. That's why secondary carbon, right? So this is secondary carbocation. And the tertiary carbocation is the carbon which is attached to three different carbons. That is called a tertiary carbocation. So talking about the stability of carbocations, tertiary carbocations are most stable carbocation among them, and after that secondary one, then primary, and then methyl carbocation. Then next, allylic carbocation is also there, where the carbon next to the double bond is carbocation, which is called a allylic carbocation. In benzylic carbocation, the carbocation is next to the benzylic ring, phenol ring. So that's why this is a benzylic carbocation. And if the next carbon of the triple bond is a carbocation, that time it will called as a propagylic carbocation. Similarly, if the carbocation is present on the double bond carbon, it is known as a vinylic carbocation, and aryl carbocation is a carbocation present on the aromatic ring. Similarly, if carbocation is on the triple bond, which is known as a alkynyl carbocation. So these are the basic introduction. SN1 substitution, nucleophilic unimolecular reaction, and even stand for unimolecular elimination. So in this case, all of you can see these three phenyl rings are bulky group. So first carbocation formation will take place because the reaction will go via SN1. It cannot go via SN2 because of this tertiary carbon. So it will become tertiary carbocation, which is the most stable carbocation because it is benzylic also and tertiary also. That's why. And then nucleophilic attack will give the corresponding product. Similarly, in this case, second case here, because one is methyl group, so elimination is possible. In this case, elimination is not possible in first case. So that's why this mechanism will go via even, stands for unimolecular elimination, even elimination reaction. So after the carbocation formation, tertiary carbocation formation, elimination will take place to form the double bond. I hope this is the basic things clear to you. Now we will solve the questions. So the first question is, among the following, which is the most stabilized carbocations? Which is the most stabilized carbocation? So here on benzene ring, you can see the substitution OH, amine, and CH3 alkyl, right? So all of you know that the on benzene ring, remember that benzene ring electron donating groups are enhancing the stability of the carbocation, and electron withdrawing group is a make a carbocation less stable. Okay, so here we can see that these groups have different electronic effects. So we will discuss one by one. So hydroxy group have lone pair, right? Lone pair of electron. So is it electron rich or electron deficient? So as it is present on the benzene ring, it will donate the pair of electron which is act as a it will act as a plus I effect. Sorry, mesomeric effect. Plus N. Okay, mesomeric effect. It will show mesomeric effect. Lone pair will push here and it will stabilize this carbocation. Okay, talking about the second one, again here also lone pair of electron is present, right? This one. So because this can also donate the pair of electron, it will make this electron rich and stabilize this carbocation. Now the third one is methyl group. Methyl group is also electron rich, but comparatively, if we are going to compare these one, so compared to the amino group and alcohol hydroxy group, this is less electron donating group, right? Less electron rich. So because uh, this is also a good group, but it will not behave as much as like hydroxy and amino. So from this we are sure that this is not the answer, because among them this is a least electron rich group. Now talking about the hydroxy and amino group, here you can see that hydroxy oxygen is very electron pulling species, electron like a electronegative atom, right? So because of that it will not share the pair of electron easily, but instead of this nitrogen will easily share the pair of electron and it will stabilize this carbocation. So the correct answer of this one is B, because the more electron rich will be the ring, the more stable carbocation formation will takes place. So that's why this carbocation is more stable among them. Now the second question is structure of triplet carbon. Okay, so here we have to find out the triplet carbon. Triplet carbon, how you will get triplet carbon? So we have to get the electron spin plus 1. Okay, so we will see the electron spin here. So in first case A, we have, okay, we will discuss one by one. Okay, so this spin is up, right? I'm writing 1. Then this spin is also up. So 1, 1 plus 1. Okay, and plus 1, then it is equal to 3. Correct? Now talking about the B one. So one electron is up spin and one is down spin, right? So one is plus, then okay, 1, and then in bracket we will write minus 1, because the other one is down spin, right? So if we will write here total, minus plus will become minus, right? So 1 minus 1 0 plus 1. So this is a 1. So this one is singlet, correct? Talking about this one, similar way, this is also minus 1 plus 1, because both are in opposite spin, right? Minus 1 plus 1 plus 1. Okay, so this is also singlet carbon, and the fourth one, here also both the electrons are opposite spin, like this way, same, right? So if you will see the all four options, or B C D all have singlet carbon, but the A one having a triplet, because of the electrons in different orbital with the same spin, up spin. Okay, so that's why the correct answer for this question is option number A. Next, among the following, which one is the most stable carbon anion? So, if we are talking about the carbon anion, The stability is exactly reverse to the carbocation. What happens in carbocation? Tertiary carbocations are most more stable compared to secondary and primary one, right? But in case of carbon anion, primary carbon anion are more stable than the secondary one, and secondary carbon anion is more stable than the tertiary carbon anion. Exactly the reverse case. So here we are going to talk about the carbon anion stability, but in this case we are not comparing the tertiary, primary, and secondary, because here we have here aromatic ring system. Okay, we'll discuss one by one. So in this case we have 2 pi electrons, right? 2 pi bonds means 4 pi electrons plus this uh, carbon anion, that means a pair of electron is here, right? So total number of electrons are in this case is 6, right? So it is coming under 4 pi plus 2 Huckel rules, right? Huckel rules of aromaticity. So here we have 6 electron. So this is aromatic system, right? This one is aromatic system. Now talking about the B1, here we have 2 pi electrons and negative charge. That means 2 electrons. Means total pi electrons are 4, right? 4 pi electrons. Now third one, C. Talking about the C, this is a primary carbocation, right? And this one is methylic carbon anion. Sorry, carbon anion. Both are carbon anion. Now let's see here. If we will compare this, D carbocation is stable because carbon anion stability is depends on the primary, secondary, that way. But here we have aromatic system A. Because of delocalization and aromaticity, this carbocation, cyclopentadiene carbocation, is more stable among them because of aromaticity. So here aromatic factor is important. And B1 is anti-aromatic. If you'll know the aromatic rule, so 4 pi electrons are giving a anti-aromatic compound, and 4 and pi plus 2 electron are giving a aromatic compound. So this is a anti-aromatic compound. So if we will talk about the order, A is the most stable carbon anion, then we'll go to the D, then C, and then B, because anti-aromatic are always the least one, least stable. Okay, so the correct answer is option number A. The next question is, predict the major product of the following reactions. So here we have condition where acidic hydrobromide HBr is there with per acid in thermal condition. Okay, so it is a there is a per acid and HBr. So if the reaction was going in absence of per acid, it would go via carbocation for addition, right? Formation. But the reaction, because per acid is present here, the reaction is going via radical mechanism. So I will discuss both the mechanism. If the reaction is going via ionic mechanism, what will happen? H plus will get added here, right? Acidic, in acidic condition, H plus will come here and carbocation will form over here, this position. Tertiary carbocation, right? Because tertiary carbocation are stable carbocation, that's why it will form tertiary carbocation. Then bromo addition will takes place. So if the reaction is going via ionic mechanism, Then this would be the product if ionic mechanism. But here we have per acid. So per acid is there, that means the reaction will go via and reaction will go via radical mechanism. So here we will see initially the per acid will undergo in thermal condition, it will form a radical. Okay, then alkoxy radical will form here, and this alkoxy radical will take the proton from HBr to form the Br radical. Okay, after the formation of Br radical, now radical addition will takes place. So in step 3, when the radical homolytic cleavage will takes place, and radical will generate on both this point. Okay, but the tertiary radical are more stable, so the primary radical will be taken by bromine radical, so this tertiary radical formation will takes place. Okay, after this tertiary radical formation, the H radical will trap this tertiary radical, and it will form the product A. Okay, so this is the reaction mechanism via radical. So both the mechanism will give the different result. If it's going via ionic mechanism, in absence of per acid, it will give this B as a product, this one. But because in here it is mentioned that per acid is there, so sorry, yeah, peroxide is there. So in presence of peroxide, it will always give a result of radical addition reaction, which is the correct answer A. Okay, because bromine radical is getting added and tertiary radical is forming here, and it will get trapped by H radical. The next question is, we have to find out the correct answer here. So in this case, we can see that the reduction is taking place in presence of potassium and ammonia. Okay, so this is the very famous reduction. Can you tell me which type of reduction it will takes place? Because it's a basic reaction, not coming in a carbocation part. So I just wanted to ask you. It is a Birch reduction. So Birch reduction have several rules. Like if you have electron donating group, then it will give a different result, and when you have a electron withdrawing group, that time you will get the different result. Okay. So talking about here in this ring, we have here donating group, and here we have ester group, right? So uh, because there is some rule, like when we have electron donating group, I will write here example. Suppose we have here electron withdrawing group. Okay, so in Birch reduction, what will be the result? we have this way double bond. Okay, after reduction we will get this result. But when we have donating group, that time what happened? So in this case we will have double bond this way. So in our question we can see that donating group is here and this is a withdrawing group, right? This ester one. So the double bond position will takes place this way, right? After this one, the second step is also given, which is isopropyl iodide addition. So this one, after getting the birch reduction, the next step will be the addition of isopropyl group. So this is a this one is a electrophilic. So because of electrophilic group, so we can see that the addition will takes place at this position because this carbon is electrophilic and this one is electron rich. So the addition will takes place here and it will give the result this one. This is the correct answer. The next question is the intermediate A in the following conversion is. So if you can see that in this case we have amino acid, right? So this amino acid, okay, so here we have amino acids. This amino acid is undergoing a reaction with sodium nitrate and HCl. So what will happen first? First the azo formation will takes place. So here we have diazo N2. N2 formation will takes place. Then this N2 elimination followed by CO2 elimination will result in a formation of benzene. Why benzene? You can see here in second step after getting A, in final product you have these two methyl group, right, which are here and here. So you are getting this methyl group. So that means this is undergoing a cycloaddition reaction. So cycloaddition reaction is 4 plus 2 cycloaddition reaction. So 4 pi electron is there here, right? That means this is acting as a dienophile, which is a 2 pi electron. So for if it is acting as a dienophile, it should have a pi bond here, which is participating in the reaction, right? This one. So if it will undergo cycloaddition reaction with this diene, it will give you a this product which is given here. So the correct answer is here A is a benzene intermediate, because here carbocation free radical and carbon anion is not forming. It is forming benzene intermediate, which is further undergoing a cycloaddition reaction 4 plus 2. Okay, so the correct answer is option number D. The question number 7 is here. The major product in the following conversion is. So here again we are going to discuss the mechanism. So here we have magnesium in first step, right? So what we'll do with magnesium? Magnesium will get inserted here like Grignard. Have you heard about Grignard reagent? Right? So what is Grignard reagent? RMGX. RMGX, correct? So X is a halogen atom always, and R is a alkyl or aryl ring. So here we have aryl ring. So magnesium, this Grignard reagent is formed by this way only. Magnesium is getting inserted between halogen and R species, aromatic or alkyl moiety. Right. So here magnesium insertion will take place and it will become Grignard reagent. After this one, this will become nucleophilic, right? Because Grignard reagents are nucleophilic, which is attacking on another electrophile. So it will attack on Grignard reagent will attack on this one and it will get knockout, right? So initially we will get Cl double bond F. Sorry, it will not get knockout, double bond. Sorry for this one. This way. Okay. So elimination of this bromo and fluoro will takes place and it will again form a benzene intermediate. Benzene intermediate. Then 2 plus 2 cycloaddition will takes place. So because 2 plus 2 in thermal condition is giving a inversion. So here we have trans stereochemistry of this dienophile. So we will get cis product because in thermal condition 2 plus 2 cycloaddition reaction is giving inversion of stereochemistry. So the correct answer will be option number B, because in first case A having a both Cl group trans, right? So it will not give a trans product because the dienophile stereochemistry was already trans. So trans will become cis in presence of thermal condition in 2 plus 2 cycloaddition reaction. So that's why A is not the correct option. Talking about the C having the both the products. So here we will get exclusively one product. both the product are possible when the mechanism is going via ionic mechanism. This is the concerted mechanism after benzyne formation. So that's why the correct answer is option number B. Then the next question is the major product formed in the following reaction. So we have here Grignard reagent, ethyl magnesium bromide, and water, acidic condition, right? So initially on cyano group, what is cyano group? C triple bond. This is nitrile group. Or this is also called a nitrile group. This one, correct? So this ethyl will act as a nucleophile and it will attack on a electrophilic center of this nitrile group. So here, so after this attack, it will become C double bond N, right? So hydrolysis will takes place. So in hydrolysis, what will happen? Water will attack, and after hydrolysis, this C double bond N group will become carbonyl. Correct? Carbonyl. Then ethyl group was there already, right? Ethyl. Sorry. This is ethyl. Okay. Then aromatic ring which was there already. So according to this mechanism, which is the correct answer? Option number B, right? Because hydrolysis is going here, that's why we are getting a hydrolyzed product, which is a ketone one. If hydrolysis was not happening, that time we might have got the option C as a product because the further addition was taking place, but because water is there, we will get hydrolyzed product. The next question is the major product formed in the following reaction. Hmm. So what will be the answer here? See here, we have zinc powder on arrow, right? So what's happening in presence of zinc? Zinc is also acting as a magnesium and it will get inserted here, right? So zinc, it will become zinc bromide first, right? Hmm. Then after this one, this will become nucleophile. So nucleophilic attack will takes place on this benzaldehyde. And after nucleophilic attack, benzaldehyde will give. OET. Okay. Okay, this benzaldehyde. Now, this nucleophile will further attack on this carbonyl center, and this ethyl group will knock out this way. Okay, so this will form five-member ring. So in this case, the correct answer according to this mechanism is option number A. Correct. Further nucleophilic attack will takes place. Because why option number B is not correct? Because this double bond is not there in product. And talking about the option number C, so this ester group will not remain as it is, it will get knockout. So that's why the correct answer is option number A. Now question number 10 is here. What are the oxidation states of sulfur in the following compound? So these are very basic question. So all of you know how to calculate the oxidation state. So for calculating the oxidation state, you have to check the species attached to the atom. So because here we are talking about the sulfur, we will check the sulfur is substituted with which atom. So here we have two methyl groups. So both the methyl groups are sharing one oxidation state, giving one oxidation state. So in this case, the oxidation state is plus 2. We are not saying plus 2 because sulfur is an electronegative group, so it's pulling the electron towards itself. So we will write the directly oxidation state. So here two atoms are connected, so two sigma bond are there, so oxidation state is 2. In case of B, so all of you know that oxygen are sharing two electrons to form the bond because double bond is here, right? So that's why here, because of this double bond, the oxidation state will become plus 2 from this side, right? Oxidation state from 2, 2 because of oxygen and 2 because of these two methyl groups, right? So 2 plus 2, 4, correct? 4. Now in case of C, we have two carbonyl, sorry, not carbonyl, I'm sorry, two oxygen atoms which are ha- making a double bond with the sulfur. So how many number of bonds are there total? 1, 2, 3, 4, 5, 6. 6, right? So that's why the oxidation state will be 6 here. So C having 6 oxidation state here, and A is having plus 2 oxidation state. So the correct answer is option number D. B is having 4 oxidation state, right? So just remember, whenever you have to find out the oxidation state, just check the atom which is attached to the atom which we want to find out the oxidation state, and also the number of bonds. So in this case, you can see only two bonds are there with sulfur, so that's why plus 2 oxidation state. Here we have 4 bonds, so plus 4 oxidation state, and here we have 6 bonds, so that's why oxidation state will become 6. Okay, next question is, find out the intermediate X and the final product P in the following reaction. So here we can see that we have sulfoxide, right? So in this case, we have sodium hydride base. So because sodium hydride is a very strong base, it is giving hydride ion, or it can abstract the proton because it's a strong base. It will not act as a nucleophile, right? So it will act as a base. So base will always abstracting the proton. So this is a strong base, right? So in this case, from where we can abstract the proton? Anybody? We can abstract the proton from this methyl or this methyl. So if we will abstract the proton from any of the methyl, what we will get? We will get this intermediate, right? We will not get this one because here hadride transfer is taking place, and this sodium hydride is a strong base. It will abstract the proton, so it will always give this intermediate, not this one. Okay. So after getting this one, this is a elide form. Now this nucleophilic attack can happen here, right? So this is our X. Then in case of P product, here we have the another reagent. This one. So bromo is a good living group. So this nucleophilic attack will takes place here in a SN2 manner here, and bromine will get knockout. It will give the product this one, right? Why not this one? Here elimination is taking place, but this halide will get substituted instead of the elimination. So that's why the correct answer is option number C. Okay. Next, addition of BH3 to a carbon carbon double bond is. So when we have the carbon carbon double bond this way, so if we will add BH3, which is borohydrate, what will happen? It will add on this olefin this way. Okay. So according to the Markovnikov rule, what happened when addition is taking place? Generally, the substitution is taking place on internal carbon of olefin. Okay, and hydrogen is going the last substituted carbon atom. So in according to this one, this is Markovnikov rule. Okay, this is following the Markovnikov rule. But why this happens? Because bromo, suppose we have here bromide. Bromide are more electronegative than the carbon atom, right? So because of that, they are adding they are getting added on this carbon atom, secondary carbon atom. Okay, but in case of boron are less electronegative compared to carbon atom. So always according to Markovnikov rule, what happens? Less electronegative atom is going on the terminal carbon, and the more electronegative atom was get added on internal carbon. Okay, but boron is less in this base3. Boron is less electronegative atom, that's why it's getting added on terminal carbon according to the rule. And hydrogen are more electronegative than the boron, that's why they are getting added on the internal carbon. But because the substitution is taking place on terminal one, that's why this known as a anti-Markovnikov of scene addition, because scene addition is taking place in this case, but because the substitution is different than the normal one, that's why it is called as a anti-Markovnikov rule. So we have discussed here various different types of questions. We will quickly revise it, and then we will discuss the few more concept, and we will solve the question based on that in next class. So today we have discussed the few questions where we have discussed the question number 1 was based on the stability of the carbocation, and we found out that the carbocation with more electron donating group are more stable. Okay, so in this case we have discussed the CH3 is a less electronegative compared to the amino and hydroxy, and NH2 group and nitrogen is more electron giving compared to the oxygen atom because of the electron donating ability. So that's why the correct answer was option number B. Then we have discussed the structure of triplet carbene, and we saw that the option number A has the both the electron in same spin. That's why the triplet carbon structure is option number A. Then we also discussed the stability of carbon anion, and we found that the aromaticity is increasing the stability of the carbon anion, and anti-aromaticity is make it a least stable one. So we have discussed the pattern, and we found that the option number A is the correct answer because of the Huckel rule, following the Huckel rule, which is aromaticity rule. And then we have discussed the product formation in this case with both the mechanism ionic as well as radical mechanism. So if the peroxide, in absence of peroxide, it is going via ionic mechanism where we will get the carbocation formation, tertiary carbocation formation followed by substitution of bromide. But this reaction is undergoing in presence of peroxide, so peroxide will form the radical here, and then that alkoxy radical will take the proton and form a bromide radical, bromo radical, and this Br radical will getting added to the double bond to form the tertiary radical, which is the most stable radical. Then this radical will be trapped by H radical to form the desired product, which is the option number A. Then we discussed the question number 5 where we have done the discuss the Birch reduction. In Birch reduction case, we are getting the double bond here and followed by isopropyl substitution, and the correct option is option number C. Then we have discussed the cycloaddition reaction where the intermediate benzene formation is taking place. So in presence of NaNO2, the N2 diazo formation will takes place. Then followed by elimination, it will give the benzene, and this benzene will undergo a 4+2 cycloaddition reaction in presence of this diene to give the corresponding product. The option number 4, A is benzene, is the correct answer. Then we discuss the one more example where we again the reaction is going via benzene intermediate and followed by 2+2 cycloaddition reaction. So because the reaction is 2+2 cycloaddition in thermal condition, that's why it will give the inversion of stereochemistry. So the correct answer is option number B. Then we have discussed the question where we have nitrile group and Grignard addition is taking place. So Grignard addition will give the intermediate, this one. Then the after the hydrolysis in presence of H3O plus, it will give the product ketone as a product, which is option number B. Then we have discussed the major product form in the following reaction. So here we have discussed that zinc insertion will takes place. Then after that one, nucleophilic attack on benzaldehyde will takes place to form this intermediate, and after getting this intermediate, the O- will attack on a carbonyl carbon and followed by the OET elimination to give the 5-member cyclic lactone formation. So here you can see that this option number A is the correct option. Then we discuss the oxidation state of sulfur in the following compound. So we have discussed the number of bonds attached to the sulfur atom are the oxidation state in short, right? So in A, we have discussed that two groups are attached to sulfur atom. That's why the two bonds are there. So that's why the oxidation state of A is +2, And talking about the B, there are four bonds. One, two, three, four. Two bonds are with oxygen, right? So that's why the oxidation state is 4. And in case of C, there are two oxygen atoms. So two bonds are here and two here. So 4 is here, and then two methyl are there. So 6 bonds are there with sulfur. So that's why the correct answer is option number D, where the oxidation state of A is 2, B is 4, and C is 6. Then we discuss the intermediate X formation, followed by the product formation. So we discussed that the sodium hydride is a strong base which is abstracting the proton instead of acting as a nucleophile. So in option number A and B here, hydride is acting as a nucleophile, right? But because sodium hydride is a strong base, it will abstract the proton instead of giving a hydride ion. So that's why in option number C and D we can see the base is abstracting the proton, right? Proton abstraction is there, but after that it will attack on a nucleophilic attack will takes place on bromide, and this carbon next to bromide and Br will knock out. So this, according to this mechanism, the option number C is the correct answer, because in D elimination is taking place, right? Double bond formation is taking place. So the correct answer is option number C. Then, after this one, we have discussed the addition of BH3 to the carbon double bond is anti-Markovnikov chain addition. We have discussed Markovnikov addition, and why this is a anti-Markovnikov addition, and this is a chain addition, right? So here we have discussed the various question from the assignment. Now in next class we are going to discuss the more things about the carbocation. But before solving the week 1 class again, I would like to discuss few things about the carbocation. So how the carbocation formation is taking place. So we have discussed the classification of carbocation, and carbocation formation is here. So there are various types of reaction. First we will discuss the homolytic cleavage. What is homolytic cleavage? In homolytic cleavage, the bond breaking is taking place and electron is distributed between both the atoms equally. That is called a homolytic cleavage. So that's why one electron will be at A position, and the another one will be there on B position. So that's why radicals formation will takes place, right? Similarly, in case of methane, if you will do the homolytic cleavage, H radical will form and CH3 radical will form. This is the homolytic cleavage. Now talking about the heterolytic cleavage is a bond dissociation where one electronegative atom is pulled the pair of electron towards itself. So if this bond is getting broken, so the if B is more electronegative than the A, it will pull both the electron towards itself. So it will become heterolytic cleavage. So here you can see that cations and anion formation is taking place. So let's talk about the heterolytic cleavage which is forming the cation. So here, if heterolytic cleavage is taking place here, so CH3 will abstract, will take both the proton and it will form anion, and cation formation will take place here, right? So this is a basic mechanism for carbocation formation. So, we'll discuss the epoxide synthesis of carbocation via epoxide opening. So, if epoxide ring opening is taking place, then the Lewis acid will bind with the epoxide oxygen, and the bond breaking will takes place to form the secondary carbocation. Okay, so this option, the next one is Friedel-Crafts reaction, where also the ketone formation is taking place. We'll quickly go through the slides and we'll see the. Now let's talk about the stability of the carbocation. So carbocation stability depends on the various factors. So first one is the hybridization of the atom. As we have discussed earlier, the geometry of the molecule changed, so the stability is also getting changed, right? Then the next one is the electronic effect, and then the structural constraint. So let's talk about the electronic effects. So electronic effects include the inductive effect, hyperconjugation, and resonance. So we'll discuss one by one everything. So here we have carbocation stabilization controlling SN1 rate. So just quickly I'm going through the slides. You can go and watch on YouTube. These classes are already taken by Professor Shantanu Panda, which is available on YouTube. So I will discuss quickly the important points. This one we have already discussed, nature of attached functional groups. I told you, if electron withdrawing groups are attached to the carbocation, then it will become less stable, and if electron donating groups are present, then it will become more stable, right? Then we have discussed the stability of carbocation. We have already discussed. Then cyclopropylic stabilization. The stabilization is because of this ring strain. This pi bond is making it stable. This carbocation is stabilized by this cyclopropane ring because of banana bond. Banana bond formation is there because of the ring strain. Okay, so that's why these are more the number of cyclopropyl ring is present, the more the stability of the carbocation. Then we have discussed the aromaticity. So aromatic compounds are more stable carbocation compared to the anti-aromatic. So here we have 4 pi electrons. So because 4 pi electrons are anti-aromatic compound, this one is a less stable. And talking about the cyclopropene carbocation, here we can see that 2 pi electrons are there, which is following the 4 and pi plus 2 rule. Okay, so that's why this is aromatic one, so that's why this one is stable. And talking about the last, this one, octatrine, in this case, because three double bond are there, it is following the rule for aromatic compound, so this one is also a aromatic compound, that's why more stable. Now we will discuss the rearrangement reaction. So, because these rearrangement reactions going via carbocation formation, that's why we are here to discuss this one. So, first one is the Wagner-Meerman rearrangement reaction. So, in this case, what happened? One two rearrangement reaction is taking place. So, a carbocation formation is taking place. Then the migration is happened, and one two sigma tropic rearrangement give the stereochemical retention of products. So we will discuss here in this case what happening here. We have hydroxy group, right? It will get protonated and it will knock out, right? After this one, carbocation formation will take place at secondary position. Here you can see. Then the migration will take place. So either this methyl group can migrate here, or this 4 5 bond can migrate here. But why this methyl group is not migrating? Because if it will get migrated, the double bond will come on the bridgehead position, which is not a stable one. Stable product. Okay. So this 4 5 bond will get break and it will get migrated here, and it will form this intermediate. Then if we will rotate this compound, we'll found that this as a intermediate, we can also write this way, and then ha- pro- proton elimination will result in a formation of double bond which will give the product A, product formation. Then we have few examples where we can see these type of rearrangement reaction. Then let's talk about the pinnacle rearrangement. What happened in pinnacle rearrangement? First, in presence of acidic condition, protonation will takes place. So after the protonation, this will H2O will knock out and carbocation formation will takes place here, right? After that, this one oxygen lone pair will push here, and the migration of the group will takes place on this carbocation. Okay, and it will give a 1,2 migrated product ketone. So this is a few examples where we can see the ring expansion. So in this case, protonation will takes place, then H2O elimination followed by alkyl migration will takes place this way, and it will give six member ring, right? So talking about the after the pinnacle on rearrangement, we will discuss the semi-pinnacle rearrangement reaction. Why semi-pinnacle rearrangement reaction is necessary? We can see that in this case we have two hydroxy groups. So according to the pinnacle on rearrangement, hydrox H2 elimination will take place and carbocation will form, which is more stable. So in primary and tertiary case, tertiary will form here, right? Then tertiary carbocation will form here, and it will not give desired product, right? Migration will not take place. So to avoid this one, what happening here, you can see this here, living group, right? After this way it will form, and highly stable tertiary carbocation will easily form, and it will not give the desired product, which is 7 member ring. So ring expansion will not takes place, right? So because of this one, to solve this problem, this primary carbocation will not form here because it's highly unstable, right? So it will not form to give the desired product. To solve this problem, one hydroxy group will be converted to good living group. This is that is OTS, otosyl group, right? So tosylate will form after elimination. This is a good living group. In absence of acid, also it will get knockout. So once it will get knockout, this oxygen lone pair electron will push here and it will get migrated. Right? Only tosyl can live in non-acidic condition. That's why this semi-pinnacle rearrangement reaction is working well in this case. So there are few examples of semi-pinnacle on rearrangement reaction. Then let's talk about the Tapni-Gemini rearrangement. In this case, nothing is changed. Only the difference is there. In semi-pinnacle on triplet group was the eliminating group, and in this case we have diazo one. So in presence of this diazo formation, after the diazo formation, it will get knockout and carbocation formation will takes place, which will uh, get converted to 1,2 migration reaction, which will undergo 1,2 migration reaction to give the corresponding compound, which is similar to semi-pinnacle rearrangement reaction. So there are few examples you can solve yourself. Now let's talk about the Mayer-Chester rearrangement. What happened in this case? because this is also happening in acidic condition. In acidic condition, protonation will takes place and H2 elimination will takes place. Now secondary carbocation will, sorry, tertiary carbocation will generate over here. Then this carbocation will trap by this double bond because of conjugation, and it will form alene carbocation intermediate. Then after this alene carbocation intermediate, water hydrolysis will takes place, and it will give you a enone formation. Okay, so even reaction will takes place to form alene. Then after alene, it will give you a, in presence of water, it will give you a enone. Let's talk about the Bear villager rearrangement. So in case of Bear villager rearrangement, what happened, per acid used, and per acid act as a nucleophile on carbonyl carbon and form the intermediate, this one. After this intermediate formation, the because the migration is taking place, it will go to this oxygen atom and this group will knock out, so it will form the ester from ketone. So migratory aptitude is also given here. So you can see the when R group will get migrated. So the bulkier the group, it will get easily migrated, right? So small group will not get migrated. So this is depends on the migratory aptitude. Then after this one, we have few examples where Baer-Villiger rearrangement is taking place. So Baer-Villiger oxidation, Baer-Villiger rearrangement, oxygen will always come towards the side of the group which can undergo a migration. So as we have discussed, the bulky group will, an electron rich group will get migrated easily. So here we have phenyl and methyl group, right? So after the Baer-Villiger oxidation reaction, the oxygen will comes between this one because this group is going to migrate, right? In this case, we have electron withdrawing group, right? CF3. So that's why the this group will not get migrated, this carbon will not migrate, so the migration will takes place from the other side, and oxygen will come in between these two carbon. The third example is fourth example is here. So here methyl group can in between methyl and phenyl group, phenyl have a good migratory aptitude, phenyl group is a electron rich, so it will get migrated. So that's why oxygen atom will come between this carbon and oxygen atom, because this group is getting migrated. This is a shortcut trick. Okay, so in this case where we have cyclohexyl and methyl, so of course cyclohexyl group is more electron rich, so that's why oxygen atom will come over here. And in the last case, tert-butyl and this phenyl group, tert-butyl is a good migratory aptitude, so oxygen atom will come over here. This is a mistake, this is not a carbon, here is oxygen atom. Okay, then we have few more examples. You can see here always the migratory group is having the oxygen insertion is always taking place between the migratory group and the carbonyl carbon. Okay, next, Beckmann rearrangement. Okay, so in Beckmann rearrangement, the trans group to the OH is always the group which is going to migrate. So in this case, this pink one is trans to this hydroxy group. So that's why it's going to migrate after the protonation and it will knock out, right? So this is the rule for Beckmann rearrangement reaction. So we can see this example where this hydroxy group is trans. So this bond is getting migrated to this one, and the ring expansion is taking place. Then H2 elimination, H2 addition will give the nucleophilic attack of this OH, which is further giving the amide formation. Okay, So simply what you have to do whenever you see this type of rearrangement reaction, there is a shortcut again. So if the trans group is there, right, this one, so you have to put the n between these two carbon and make it carbonyl, right, like this one. So because this group is going to migrate, which is trans to this hydroxy group, right. So overall you will get this amide. Then there are few examples, you have to solve it by yourself, and you will get the trick to solve this one. Okay. So for today lecture, I think I should stop here. We will discuss the few more detailed question based on the rearrangement reaction in next class, and question based on carbocation also. If you have any question, any doubt regarding this, you can ask me in next class. Every Friday we are going to have a class from 7 to 9 p.m., and make sure I will make sure with the connection, and the issue with the laptop should be resolved before the class. So today we have faced so many issues with technical issue with the laptop. Sorry for the inconvenience. So I'm going to end today's class here. Let's meet next week. Thank you so much for your kind attention. Thank you.